Dear students, you are all into the 7th session on power electronics. You have been introduced to various semiconductor devices, various turn on methods of SCR, various turn off methods. You know SCR is a unidirectional device, and you know SCR is a latching device. To turn on an SCR, you have already studied different methods. You know the method of gate triggering. In gate triggering, we have a DC gate triggering, AC gate triggering and pulse triggering. And you already know the pulse triggering is the most efficient method of triggering an SCR. In pulse triggering, train of pulses is the best method of triggering an SCR. Once SCR is into conducting state, once your SCR is triggered by a gate, it loses the control. So, you know how to turn off an SCR by different methods. If you in last classes you have seen, if the supply voltage is AC, SCR is turned off by natural commutation. If the supply voltage is DC, you need a force commutation, and we have discussed different methods of force commutation: self commutation, complementary commutation, pulse impulse commutation, external pulse commutation and all. Now, today I will be dealing with phase controlled rectifiers. In phase of control rectifiers, these are the topics I am going to discuss. The principle of phase control rectifier, single quadrant semi converter, two quadrant full converter, dual converter and the line commutation. It's already studied in commutation, but I again will revise that one here also, because we need line commutation for phase controlled rectifiers. Now, you already know what is rectifier. Rectifier is a process of converting AC to DC. Different methods you can convert using the following devices: diodes, thyristor, power MOSFET. In rectification, we convert AC to DC. That we have different methods. Rectifier circuit can be classified as uncontrolled rectifier circuit, controlled rectifier circuit. In uncontrolled rectifier circuit, we have no control over the output voltage. We cannot vary the output voltage. The uncontrolled rectifier circuit, we use the circuit element as a diode. This is what I made it in the first class on MOSFET and IGBT. The diode is an uncontrolled device where you do not have any control. You do not have control on turn on and turn off. So, using uncontrolled rectifier circuit, your output voltage will be fixed. You can't vary its output voltage. So, then comes the controlled rectifier circuit, which we can do by using thyristor. You already know how this SCR is helpful here, because we can control the firing of an SCR. You can exactly fire at the desired angle. If SCR is fired at 0 degree, we will get a maximum output voltage. If SCR fired at 180 degree, we get a minimum output voltage. So, this is how we can control the output voltage in a control rectifier circuit. This finds an application in industry, because we need a variable DC output voltage in most of the applications. Maybe in paper mills or textile mills, where you need a variable DC supply to drive the DC motors, or in application like HVDC, or in power drives of portable devices. All you need a variable DC supply. So, whenever we need a variable DC supply, we have to go for a control rectifier circuit. So, when you need a fixed DC supply, we can go for uncontrolled rectifier circuit. Now, see the power AC input. So, if you want a constant DC voltage, the circuit element that we are going to use, the power semiconductor device, the device is already familiar with. which power semiconductor devices are called, or they are termed as the heart of power electronics, because in all power electronics equipments we find one of the devices, depends on the nature of application or depending on the nature of equipment, we have any one of the power electronics devices. We have studied the diode, thyristor, MOSFET, IGBT. In the first 3 sessions on power electronics, you have been introduced to all the devices. Now you already know the VI characteristics of all those devices. The thyristor, already I made it the point clear. For variable DC output voltage, we use a power semiconductor device thyristor. Thyristor is useful because we can fire it at a desired angle, so that we will get a desired output voltage, that is a variable output voltage. In controlled rectifier circuit, again classified as half controlled rectifier circuit, fully controlled rectifier circuit. In uncontrolled and half controlled rectifiers are called unidirectional converters. What do you mean by unidirectional converters? Here the power flow is from source to load, that is they are called as unidirectional converters. That means they work in a first quadrant. In fully controlled rectifiers, they are called as bidirectional converters. Here the power can flow from source to load and as well as from load to source. The phase control converters provide either 1 quadrant, 2 quadrant or 4 quadrant operations. So, that is an advantage of phase control converters, whereas in uncontrolled they work in only one direction. The phase control converters have the flexibility, you can make them work in 1 quadrant or 2 quadrant. 1 quadrant means both output voltage and current are positive. In 2 quadrant, the output voltage may be positive, may be negative, output current will be positive. In 4 quadrant, the output voltage or voltage or current either positive or negative. We will go into details later in the slides. So, already told you why we are going for phase controlled rectifiers. So, in industry applications requiring controllable DC power, we invariably use phase controlled rectifiers, because we want to output voltage to be DC power to be controlled, it cannot be constant. So, the main one of the important application are traction systems working on DC, where you need to control the speed of the motors. Again, paper mills, textile mills, steel rolling mills employing DC motor drives. Again, portable hand tool drives, where you need a DC, variable DC supply. Electromechanical and electrometallurgical process, they usually use DC supply. Again, HVDC, for transmitting high power, we are going for very high voltage DC transmission, direct current transmission. These are some of the applications requiring controllable DC powers. So, that is why we are studying the phase controlled rectifiers. If somebody asks why you are studying all these things, phase controlled DC power, these are requiring industrial applications where you need to control the DC power. We cannot have a constant power, we cannot have applications working on a constant voltage. When you need a variable DC voltage, we have to go for controllable phase controlled rectifiers only. The beauty of the SCR is we can fire the SCR at a desired firing angle. That is the beauty of SCR. Let us take up the principle of phase controlled converter operation. So, figure shows a thyristor T excited by a voltage source and it is connected to the load taken is a resistive load. When a thyristor is turned on, how to turn on a thyristor you already familiar with, you already know, and the lab also we already I think conducted experiments on thyristor. So, how to turn on a thyristor, the first condition is must be forward biased. The anode is made positive with respect to cathode. So, whenever thyristor is forward biased. So, whenever thyristor is forward biased, it does not conduct. What are other condition thing, other requirement is we need to fire the SCR, we need to give the supply to the gate. One of the firing of SCR already familiar is gate firing using the gate voltage, or you can use the pulse also. Pulse triggering is also one of the methods. Usually in the lab we give the gate supply, constant DC supply. So, when the SCR is fired, when first thing condition is it should be forward biased, anode is made positive with respect to the cathode and it is forward biased. When you apply the gate signal, that is when firing the SCR at a desired angle, the SCR conduction takes place. When SCR is fired, it starts conducting, it connects voltage source Vs to the load. Until that, Vs is not connected to R. Only when SCR is fired, voltage source Vs is connected to the load R. So, Vs appears across R. Vs source is connected across load resistance R. So, how long this SCR or thyristor conducts? Can you guess? When it will get turned off? The thyristor gets turned off naturally when the supply voltage becomes 0, it is reverse biased. This is known as natural commutation, because it is thyristor is commutated naturally. So, already seen what is commutation. Commutation is a process of turning off of a thyristor. So, this is a method of natural commutation. We are turning off the thyristor by natural means. It will get whenever voltage source becomes negative during the negative off cycle. So, thyristor is reverse biased. Reverse biased, another condition already told in the commutation class, sufficient time to enable it to move from forward conducting mode to forward blocking mode to forward conducting. That is a sufficient time. Of course, 0.01 second is sufficient time, will reverse bias it, it will move to the blocking mode. So, thyristor is commutated. With the negative off cycle, we will not get any output voltage because it reverse bias, it is turned off. So, we are getting a rectified output. So, this type of thyristor, this type of connection where you are getting only half wave, this is half wave rectifier maybe. So, again summary of sequence of units that takes place. Already told you, during positive half cycle of input voltage, thyristor forward biased. When T1 is fired at omega t is equal to alpha, T1 conducts and the input voltage appears across the load. The input voltage starts to be negative at omega t is equal to pi. T1 is reverse biased and T1 gets turned off. The time after input voltage starts to go positive until the thyristor is fired is called a delay firing angle. This is very important definition. How to define a firing angle? The firing angle defined as the time after input voltage starts to go positive. This is important, or the instant at which it gives a maximum positive voltage, maximum voltage. That also you can define. The voltage starts to go positive until the thyristor is fired. That duration, that time, that angle is called the delay firing angle. So, when you fire the thyristor at omega t is equal to alpha, where omega t is equal to 0, we get a maximum voltage. At omega t is equal to 180, minimum voltage. So, omega t is alpha is called the delay or firing angle. So, this type of thyristor, this type of converters works in single quadrant. The output voltage is positive, the output current, the load current will be positive. So, this operates on single quadrant, and this type of converter we have a high ripple because it conducts only in one direction during positive half cycle only, and during negative half cycle no output voltage, it has high ripple content, therefore, it is not used in industrial applications. You can see the waveforms. So, here the thyristor is fired You see the angle alpha. How alpha is measured? From the instant it starts going positive on the instant at which thyristor is fired. This is called the firing angle alpha. So, by varying firing angle alpha, you can made to conduct from any at any point here, 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 here. So, this is output voltage. If you fired an SCR at this point alpha, so this is the output voltage you will get alpha to pi. So, at angle pi, so it is the SCR, the thyristor gets reverse biased. It is reverse biased here. See the voltage across the SCR is reverse biased. So, the current and the voltage will be 0 here. See the current. Current follows the voltage waveform because it is a resistive load. See, when in up to firing of thyristor alpha, see here the voltage across SCR will be this one. This is the voltage across SCR till the firing angle alpha. Once SCR is fired, see the voltage across SCR will be 0 because it is conducting. So, this is a point should be noted. So, whenever SCR is conducting, the voltage across SCR will be 0. When SCR is not conducting, this is a portion of voltage available. Again, in the negative half cycle, it is not conducting, voltage across the SCR it appears. This is same as input voltage. So, you can see all this in a CRO. I think already might have observed in the lab. So, by varying, so principle of apply phase controlled can better illustrated here. See, by varying the firing angle alpha, if your alpha is here now, so this is the voltage available across the load. If this is firing angle is here, this is the voltage available. Suppose firing angle becomes 0, no voltage apply is available. So, current is also same thing. So, by varying the firing angle, you can vary the output voltage. This is the principle of phase controlled rectifiers. By firing the SCR at a desired angle, so you can get the desired output voltage, or you can vary the output voltage. Already told you this type of converters are not normally used in industrial application because its output has high ripple content and low ripple frequency. High ripple content in the negative half cycle, output voltage is 0. So, there are that is a high ripple content. So, let us take up another one, single phase semi converter. So, look at the circuit diagram. So, we have in first term and first leg we have one thyristor and a diode, thyristor T1, diode D2, again thyristor T2 and D1. We have a freewheeling diode connected across the load, we have a RL load. This is the output voltage across the load. So, here the load is assumed to be highly inductive. When the load is highly inductive, the current is almost constant, I naught. Let us see the operation. We have some 4 modes of operation. We will see the 4 modes of operation now. Again, this type of converter works in first quadrant, where output voltage is positive and output current is positive. See the mode 1 operation. During period when omega t is greater than alpha and less than pi. When during this, when the SCR now the T1 is fired at omega t is equal to alpha, see the diodes T1 and D1 conducts. In first term T1, in the second term diode D1. You can see the circuit. See the T1 D1 opposite one. Next one to T2 D2 converts. So, T1 D1 this combination T2 D2. So, during this period omega t is equal greater than alpha less than pi, the T1 D1 are forward biased, and when thyristor is fired at omega t is equal to pi, it connects source, the T1 D1 connects source to the load. See the direction of current I naught and I naught is equal to Is. Is is positive here, current is I naught. And here the load stores the energy. So, now supply voltage is connected to the load RL, now inductor stores the energy in this mode 1. So, what are the observations you made in mode 1? T1, D1 are forward biased, the conduction takes place through T1 and D1. The load voltage is given by V naught is equal to V sin omega, that is supply voltage appear across the load. Inductive load stores energy, the flow of power is from source to load. If you want to go through the previous one, here the flow of power is from source to load. The flow of power is from source to load. Now, take up the mode 2. So, now the angle, firing angle, in the previous case we have taken alpha to pi, now pi to pi plus alpha. This is another important mode here. So, during the pi and pi plus alpha, what happens? Your T1 and D1 are turned off because they are reverse biased. Now, the freewheeling diode gets forward biased. So, now the source is disconnected from the supply, Is is equal to 0. So, the freewheeling, now diode is freewheeling, now the current flow, current through the load is continued, that is called the freewheeling operation. That is the use of freewheeling diode. Actually, during this duration, your source is not connected to the load. So, your freewheeling diode gets forward bias, the current through the load is continued, that is I naught. Here V naught is equal to 0, Is is equal to 0. So, observations, what are the observations you made? Input voltage is negative during that duration. So, T1 and D1 are off because they are reverse biased, T1 and D1 are off. Freewheeling diode is forward biased. Freewheeling diode conducts to provide a continuity of current in the inductive load. The load current is transferred from T1 and D1 to freewheeling diode. So, these are the observations in the mode 2. In the mode 2, remember the duration is pi to pi plus alpha, supply voltage is negative, freewheeling diode comes into picture as forward bias, the load current flows through the freewheeling diode, provides a continuity of current to the inductive load. Now, load current is transferred from T1 and D1 to freewheeling diode. Now, mode 3. So, mode 1 is alpha to pi, mode 2 is pi to pi plus alpha. Now, mode 3 pi plus alpha to 2 pi. What happens to the pi plus alpha to 2 pi? The thyristors T1 and D1 already off. Here the freewheeling diode also off here. So, now T2 and D2 are forward biased and they are fired at this angle pi plus alpha. Now, it connects source to the load. Now, source is connected to load RL load through the thyristor T2 and D2. See the flow of current, direction of flow. The source current is negative, but voltage is source current, but output current is positive only. See the direction of output current, it is positive only. Let us see the observations. Here again load stores energy in this mode. Let us see the observations. During negative half cycle of T2 and negative half cycle, the T2 and D2 are forward biased and is fired at omega t is equal to alpha plus pi. the freewheeling diode is reverse biased here and DFW is turned off. The load is connected to supply through T2 and D2. Now, this is again mode 4, that is from 0 to alpha. So, omega t is pi less than 2 plus alpha or 0 to alpha. Here again the freewheeling diode comes into picture. Here again the supply current Is is equal to 0. See the observations of mode 4. The supply voltage becomes positive, the freewheeling starts through freewheeling diode, the load voltage is 0 and supply current is 0. During freewheeling diode operation or during the duration during which the freewheeling diode works, the load voltage will be 0 and supply current is also 0. These are the waveforms. See the supply waveform here, it is fired at an angle alpha. This is called the firing angle. This is the output voltage which appears between alpha and 2 pi. Between pi and alpha plus phi, this is freewheeling diode operation, no voltage appears across the load. So, this is the thyristor current, duration between alpha to pi, this is thyristor current I2, T2 and this will be T1 and D1 works. So, here it is, this is this is a ID1, so it works between alpha and pi. This is ID2, works during duration alpha plus pi to 2 pi. This is current Is will be positive, alpha to pi and negative here, but total load current will be positive. This is a total, this is load current, this is will be constant because of inductive load. Because of inductive load, assume to highly inductive and current is constant I naught. So, these are the various waveforms for semi converter. See the load voltage, output voltage here, V naught appears only during alpha to pi, again alpha plus pi 2 pi in the freewheeling diode operation, but load current will be constant at I naught, but output voltage will be 0. See the average output voltage VDC, what is important is given by Vm by pi into 1 plus cos alpha. So, if you put alpha is equal to 0, the output voltage VDC is 2 Vm by pi. So, that is the maximum voltage that you will get. The DC voltage varied from maximum value 2 Vm by pi to 0 by varying alpha from 0 to pi. When alpha is pi, what happens? You will get 0. So, maximum voltage is obtained when alpha is equal to 0, maximum voltage. The average output voltage will be maximum when alpha is 0. This is important thing, already told this one. When alpha is 0, the VDC, output voltage VDC is equal to 0. When alpha is pi, when alpha is 0, we will get a maximum output voltage VDC. I will repeat, when alpha is equal to 0, average output voltage will be maximum. When alpha is equal to pi, the VDC becomes 0. This converter has fairly good power factor due to the freewheeling diode, and it is commonly used in application up to 15 kilowatts. The semi converter, the single phase semi converter used in industrial applications up to 15 kilowatts. So, I will table all the modes, still the things become clear here. This is a mode 1 operation, alpha to pi. The second mode, pi to pi plus alpha. Third mode, pi plus alpha to 2 pi, 0 to alpha. See conducting devices T1, D1, alpha to pi is already seen the waveforms. So, during the second mode of operation, the freewheeling diode conducts. In third mode, again T2, D2 conducts. In fourth mode, again freewheeling diode conducts. The load voltage is positive during alpha to pi, again 0 during freewheeling diode operation, again positive 5 plus alpha to 2 pi, again 0. the load current is positive for all the 3 modes. When here it is 0 because SR is not fired here. So, the load current is constant at I naught and is positive. See the power flow here, it is source to load here in the freewheeling diode, here again source to load freewheeling diode. So, that is why this operates in first quadrant only, one quadrant converter, single quadrant which operates in first quadrant only. That is, the load voltage is positive and load current is positive, both are positive here. Now, let us take up the single phase full converter. The single phase converter, see the difference with semi converter. So, there we had a diode here, diode here. Now, in all the we have a 4 SCRs here, in all the arms 2 SCR, 2 SCRs are there. This is called single phase full converter, or it is a 2 quadrant converter. Here the power flows from source to load and as well as from load to source. We will see how it works. Here again during positive half cycle of operation, T1 and T2 conducts. Again because of highly inductive load here, the thyristors T1 and T2 they continue to conduct till pi plus alpha, that I will show you later. So, during negative half cycle T3 and T4 are forward biased and they fire at omega t is equal to pi plus alpha. So, this already told, it is a 2 quadrant operation. So, this is a rectifier operation, inverter operation. The rectifier operation, both output voltage as well as the current are positive rectifier. Here the voltage is negative, current is positive, the power is negative. So, it is power flows from load to source, that is inverter operation. So, VDC is given by 2 Vm by pi cos alpha. So, when alpha is 0, we get maximum voltage. So, these are the waveforms. This is a input waveform sinusoidal voltage. So, again your thyristor T1 and T2 are fired at angle of this angle. I told you the combination is T1 and T2 conduct simultaneously and T4 conducts during duration. Alpha is fired at this angle, omega t is equal to alpha. So, this is the output voltage we will get. Because of inductive load, the thyristor T1 and T2 continue to conduct till pi plus alpha. See the current now, the source current and this is the load current. Load current is continue, it is constant. The entire duration, this is the load current, it is constant. This is the load current I naught. See the current source current here, it is positive during duration alpha to pi plus alpha. Your source current Is is positive during duration of thyristor conduction, during duration in which the thyristor T1 and T2 conducts alpha to pi plus alpha, your source current is positive. Of course, here your voltage is negative, but source current is positive. Again the other two thyristors T3 and T4 are fired at this angle. At the same time the T1 and T2 gets reverse bias, they are turned off. See the waveform of output voltage, again it is going negative here and load current remains constant and Is becomes negative here. Let us see the observations what you can make. Now, load is highly inductive, so that load current is continuous and ripple free. During positive half cycle, the T1 and T2 are forward biased. When T1 and T2 are fired simultaneously at alpha, the load is connected to input supply through T1 and T2. Due to inductive load, T1 and T2 will continue to conduct beyond omega t is equal to pi even Vs is negative. During negative half cycle, the T3 and T4 are forward biased. Firing of T3 and T4 will apply supply voltage across T1 into the reverse blocking voltage T1 and T2 are turned off. Now, let us see the operation summary of full wave converter. Let us take the period, two periods are available now, omega t greater than alpha and less than pi, omega t greater than pi and less than pi plus alpha. The source voltage during this duration omega t greater than alpha and pi are positive, and so voltage will become negative, but source current remains positive. You will see in the waveform already told you, during the entire duration alpha to pi plus alpha, the source current IS remains positive. The power flow is from source to load during the duration alpha to pi. The power flow during the duration pi to pi plus alpha is load to source. So, the mode of operation during duration alpha to pi is rectifier operation, because both source and the voltage and current are positive. So, it is inversion operation because power flows from load to source, hence we have a two quadrant operation. So, application of single phase full converter, it is used in industrial applications up to 15 kilowatts. Now, let us take up the single phase dual converter. So, in full converter we have seen two quadrant operation, rectifier operation and inverter operation. So, if I want to have a dual converter operation, you can use two converters, full converters back to back. See, this is a converter 1, this is a converter 2. See the direction, this is anti-parallel. See the direction how the diodes are connected, T3, T2, T1, T2, T3, T4. The positive converter, this may be negative. So, T2, these are in anti-parallel with the direction of connection of this T1, T2, T3, T4. So, we use a circulating current method. There are two types of dual converters, one is with circulating current, other is without circulating current. If you go for circulating current type of dual converter, we need reactors, two reactors connected as shown in the figure. The circulating current does not flow in the load. We use the reactors only to limit the circulating current. If we do not use circulating current methods, the converter 1, either one converter can work at a time. If a converter 1 works, converter 2 will not work, gate pulse are removed. If this is works, this does not work. Here if the converter 1 can work in the inverter mode, so rectifier mode, converter 2 can work in a inverter mode. If we want both the converters to work at a time, we have to go for circulating current. If you are using any converter at a time, you need not use the reactors here. So, in applications where we need a continuous reversal of current through the load, then you have to go for a circulating current mode. So, this one is a full converter, this another a full converter. They are connected to back. So, for dual converter is nothing but a single phase full converters. You can see the voltage waveforms, sinusoidal voltage Vm, this output voltage V01 and V02. This is a converter 1 output and converter 2 output. So, if you add 0 V01 V02, this is a voltage we get. Because of this voltage we will get a circulating current. This again here alpha 1 plus alpha 2 must be equal to 180 degree. Suppose converter 1 is fired at 60 degree, the converter 2 is fired at angle 120 degree. So, converter 1 will be operating as rectifier, converter 2 will be operating as inverter. If both are required to operate at the same time, we have to go for a circulating method of dual converter. So, let us see the important points. Let us summarize the single phase dual converter. So, here the two full converters are connected back to back, both output voltage and load current flow can be reversed. The system will provide a 4 quadrant operation and it is called a dual converter. The dual converters are normally used in high power variable drives. The delay angles are controlled such that one converter operates as a rectifier and other converter as an inverter. The dual converters can be operated with or without circulating current. Without circulating current operation, only one converter, already told you, one converter operates at a time and carries the load current, and other converter is blocked by inhibiting gate pulses, by removing gate pulses. This circulating current maintains the continuous current conduction of both converters over whole control range independent of the load. The power flow in either direction at any time is possible. So, in dual converters works in 4 quadrants. So, one converter 1 can work in rectifier mode, inverter mode, converter 2 rectifier mode, inversion mode. So, that we have a 4 quadrant operation. In quadrant 1 operation, both voltage and current are positive. So, in quadrant 2 operation, your current will be negative and voltage is positive. Quadrant 3, both are negative. Quadrant 4, so one will be positive, other will be negative. So, these are the 4 quadrants of operation in a full dual converters. So, see the quadrant operation is shown: converter 1 rectifier, converter 1 inverter. So, converter 1 rectifier V naught, I naught are positive, converter 1 inverter. So, IDC is positive, I naught is positive, output voltage is negative. So, here converter 2 rectifier, see both are negative. So, this is a rectifier mode. Converter 2 inverter, so VDC is positive, current is negative. So, VDC 1 is given at 2 Vm by pi cos alpha, VDC 2 is given 2 Vm by pi cos alpha 2. So, both our voltage are in out of phase. Cos alpha 2, both are one is positive, other one is negative. Cos alpha 2, this is a minus cos alpha 1, alpha 2 is given as pi minus alpha 1, or alpha 1 plus alpha 2 is equal to 180 degree. This is an application of dual converter DC drives. Of course, we have used in a 3-phase supply here. This is an show how you use a dual converter for DC drives. If you want to rotate the direction of rotation, you can use this type of converter. In DC drives, normally if you want to rotate the direction of rotation, invariable is required. In such cases, we have to go for a dual converter DC drive. So, sometimes if you are working a generator mode, the power is fed back to the supply, then such cases also we need to go for a dual converter. So, what are the conclusions we can make in a phase controlled thyristors? The thyristor converts provides a controlled transfer of power between the line frequency AC, adjustable magnitude DC. So, already told you where we are when we are using phase control rectifiers in applications where we require a variable DC power. The applications already told you: traction system using DC, HVDC, textile, paper mills, the portable devices, variable supply. By controlling alpha, the transition from rectified into inverter mode of operation can be made and vice versa. The thyristor converters are mostly used in high power levels. The thyristor converters inject a large harmonics into the utility system. So, this is a problem with power electronic equipments or power electronic devices. All the power electronic devices, all power electronic systems, they inject harmonics to the utility system. What do you mean by harmonics? The harmonics may be first harmonic, second harmonic, the power frequency will be multiple of 2. Second harmonic means the frequency of 2 will be twice F1. The frequency increases. Frequency increases means your impedance or reactance increases, the voltage drop more. And also if you add up all the harmonics and if you see the resultant voltage, it will not be sinusoidal. And all the devices have been designed so that your source voltage must be sinusoidal. So, it pollutes the power system. All the power electronic devices, this is one of the disadvantages. It has got more advantages power electronics. This is one of the disadvantages of using power electronic devices. They introduce or they inject large harmonics into the utility system. It makes the waveform not non-sinusoidal, which affects operation sometimes. It may affect relay operation also. When the sinusoidal, the input is not sinusoidal, it may sometimes affect relay operations, faulty operations of relay. Again, voltage drops will be more. The devices may not operate properly because of harmonics in the utility system. Of course, there is a remedy for this. You can use filters so that the corresponding harmonics will be removed from the supply system. The last topic in the session is natural commutation, line commutation, which is already familiar with. Already this phase control rectifiers invariably use line commutation because the source supply is supply is AC. So, whenever a supply voltage is AC, so naturally we have a negative off cycle. So, negative off cycle with thyristor T2, the thyristor T get reverse biased and it is commutated and thyristor is turned off. To turn off a thyristor, we have two conditions. One is the current must be reduced below the holding current, which already you know the holding current is associated with turn off process. So, when current goes below holding current, again when it is the thyristor is reverse biased for sufficient time to recover its forward blocking mode. So, that is the principle of natural commutation. These are the points already you know. Source voltage is AC here, thyristor goes through natural 0, the reverse voltage appear across thyristor, the device is turned off due to natural behavior of the source voltage. One of the application already seen, the phase control rectifiers, the AC voltage controllers and the cycloconverters. AC voltage controller means we are get a variable AC voltage, input is AC, output is AC, but variable output voltage. In phase control rectifiers, just now we have discussed all the types of single phase control rectifiers, where your input is AC and output is variable DC. Cycloconverter, here it is a frequency converter. The supply frequency is 50 hertz. So, you can have a step down cycloconverter or a step up cycloconverters, where you get a variable frequency AC supply. So, these are the applications of natural commutation. So, these are how natural commutation works here. So, the thyristor is this already you know, just as sort of a revision there. So, here the thyristor is fired using pulse firing. The voltage appears across the load during duration alpha to pi. We have taken a resistive load. Again voltage appears in the negative positive half cycle. Again positive half cycle of the second cycle. This is the duration where our output voltage, so where the voltage across SCR. When thyristor is not fired, voltage appear across SCR. So, voltage across SCR will be 0 when thyristor is fired. Voltage across during negative cycle, the entire voltage appears across the SCR, because it is reverse bias, it does not conduct. So, natural commutation takes place when the input voltage is AC. So, this is one of the application of cycloconverters. So, input is AC here, output is AC, but different frequency. So, this is a positive converter, this is a negative converter. So, this may be work, this positive converter for works the duration T naught by 2, this works for duration T naught by 2. So, we are getting during this duration we get a positive pulses, rectified output, this negative cycle will get a rectified output. So, that the frequency will get reduced. Anyway, this will take up in another next coming classes, but this is an application of natural commutation. Wherever input voltage is AC, we go for natural commutation. So, what are the questions that can appear in this topic, control rectifiers? What is a phase control rectifier? The phase control rectifier, we use SCR and we fire by varying the firing angle of an SCR, we will get a variable output voltage. So, that is what we call a phase control rectifier. So, where do you use phase control rectifiers? We use a phase control rectifiers where a variable DC power is applied, required. The applications we have seen traction, HVDC, textile mills, paper mills, portable devices. So, another question with descriptive question, explain single phase semi converter with neat circuit diagram and waveforms. So, single phase semi converter, in one arm we use one thyristor diode, another arm thyristor and a diode, that is semi converter, that is single quadrant converter. Explain full converter with neat circuit diagram and waveforms. The full converter works in a 2 quadrant operation. So, inverter mode, rectifier mode. So, another question, likely question in this section, dual converters with neat circuit diagram and waveforms. In dual converters works in 4 quadrants. Dual converter works in 4 quadrants. That application you already seen in the DC drives. So, these are the topics we have covered. Thank you. Have a nice time.